Network virtualization might sound like a trite topic at this point because the industry has been doing it. But today we're going to talk about how we are virtualizing hundreds of thousands of GPUs in our cloud network. Before we go into further, I need to explain what GPU network is first. Every machine that we ship here in Google Cloud has direct connectivity to the front-end networks, and then it's connecting the machine to all the other compute or storage machines, and eventually to other data centers or the internet. But these accelerator machines built with GPUs also have a separate dedicated backend GPU to GPU connectivity called our GPU networks. It's a dedicated network, but it's also shared among the customers and tenants in the same cluster. So the state-of-the-art technology that ensures reachability isolation among these tenants sharing the GPU network has been, the fabric or switch-based isolation technologies such as VXLAN or VRFs. These technologies definitely have been useful in the early days of GPU networking because it offers reachability isolation, but we are now observing the change in customers' demand in terms of scale and feature set and security requirements. By scale means that the number of isolation groups that we need to support keeps growing very rapidly. So we may soon need to deal with hundreds of thousands or even millions of isolation groups in a data center. Feature set, we need to support now 5-tuple-based firewalling and other more esoteric capabilities. And security, the ML workloads are now increasingly running very customer-sensitive data traffic. And also, these machines can be co-located in not so trustful data center location. So we have to ensure better security here. So the solution for this that we're proposing is network virtualization. And then you may think that network virtualization is kind of known technology because all the cloud service providers have been doing this for their front-end network almost the last decade. It started with software-based network virtualization stack along with SDN, and it got accelerated. But the key problem that we need to solve additionally today in the context of GPU network is the performance and availability issue. ML workloads are notoriously sensitive to latency and bandwidth, provisioning issues. So we really have to make sure that there is very little overhead in terms of those things. And also, they're very sensitive to loss of availability. The moment you lose one single GPU network connectivity, the whole training jobs need to stop for tens of minutes, if not hours. So we have to make sure that our software releases and upgrade and maintenance needs to be very smooth. So we're going to talk about how we're solving these problems by using accelerated network virtualization stack that we have built along with our partner. And then we're going to talk about more of the details. Before we go into the details, let me first describe or give you the high-level overview of our latest B200 GPU-based offerings. It's called A4 systems. As you can see here, we are building pods of A4 machines here, and then these machines are connected to two different types of networks. The purple portion is the regular data center network, and then the green portion is the GPU network, the one that I mentioned as a separate dedicated network. And then it's rail-aligned, optimized AI fabric. And then this whole cluster is offered through the cluster director capability, which essentially offers the illusion of one big, supercomputer capability for our customers. So as I mentioned, the layer where we need to introduce network virtualization is not at the first hop switch, is actually at the machines, especially the GPU NICs. So that's where the virtualization stack is necessary. And then an individual A4 machine would look like this one at a very high level. So as you can see here, there is a A4 VM, which represents the CPU of these machines. It's connected to the front-end side NIC, which we call Google Titanium NIC. It's our smart NIC, connecting this machine to the regular data center network. It has two other accelerator connectivities. It's of course connected to the B200 GPUs. It's also connected to the GPU NIC that we have chosen for this system, NVIDIA CX7 NICs. So those green parts are the AI fabric connectivity portion. As we mentioned, we already have our smart NIC-based accelerated network virtualization stack running on this Google Titanium NIC. But today we're going to talk about the other portion here, how we have virtualized this network starting with CX7. Then I'm going to hand this over to Weilong for that.
Thanks, Chang. Next, I will talk about how we virtualize each of the GPU NIC at Google with PSP encapsulation and encryption. And after that, I will also talk about how we make this GPU network easy to operate and troubleshoot for both our customers and for Google. Let's start with some of the context of virtualization. So the primary goal for virtualization for this GPU network is to provide multi-tenant isolation, and only a subset of the traditional virtual private cloud features apply to this network because the GPU network is east-to-west only. And the primary mechanism that we use to provide multi-tenant isolation is through encapsulation. And here at Google, we use the PSP security protocol to do this. PSP is an open technology. It provides confidentiality and integrity for all of the packets that flow through this GPU network. And aside from multi-tenant isolation, we also need another set of features from the virtualization stack. For example, we want rich telemetry for monitoring the NICs and the network. We also want the ability to do in-service software updates. This is the Hitless upgrades, which I'll talk about later. And some of the features in the traditional VPC, like firewalls, are also coming to the GPU network with emerging needs. Let's zoom in on one of the GPU NICs at Google. So we operate the CX7 device in SR-IOV mode. It comes up with a physical function in a hypervisor and a virtual function. We pass this virtual function to our GPU VM. This is where our customer runs the RDMA stack and typically NICL on top of that to do machine learning jobs. In the hardware, we have a programmable block called accelerated switching and packet processing, short for ASAP2. Over the PF in the hypervisor, we use the Dokaflow SDK to program this hardware. And on top of that, we have our own daemon, which we call ASAPD. You can think of ASAPD as the layer that translates the Google control plane signals to the programming in the hardware. And with Dokaflow SDK, what we're dealing with is a collection of C libraries with APIs to program match action tables in hardware. And this is a very flexible and powerful programming model. It allows us to create a processing graph for all packets by forwarding packets between the ports, either on the VF or on the wire, and the pipes that we create in the hardware. So a basic encapsulation application at Google looks like this. We pump through all the VM egress packets or packets that are trying to leave the VM to reach other VMs, and the wire ingress packets or packets that arrived on the wire trying to talk to this VM through the root pipe. In the root pipe, we match packet metadata and some of the packet headers to decide where this packet is trying to go and what it's trying to do. If it is a packet that is trying to leave the VM, we send it to the egress PSP pipe, where we do encapsulation and encryption before we put it on the wire. And if it is a packet that is coming from the wire and trying to reach the VM, we put it through the PSP decryption first, then we do decapsulation and echo rules check, and then we forward it to the VF. Now, the key question is, how much overhead does this encapsulation and encryption add to the GPU workload? I'll hand over to Chang to talk about some of the interesting numbers we see at Google.
Great. Now that Weilong has talked about how we have network virtualized this GPU NICs, let me talk about how well we are doing it in terms of performance. The performance overhead can come in two factors. The first is bandwidth overhead, and the second is latency overhead. The bandwidth overhead is simply just the number of bytes that we consume to add additional packet headers, and then those are usually negligible, and especially with the increase of network bandwidth, link bandwidth, people usually do not worry about that. But let's look at the latency penalty here, because ML workloads, as we said, extremely latency sensitive. So here on your right, we're presenting two bar charts they're both showing the intra-rack latency between two GPU NIC endpoints. And then one is P90 latency, the other is P100, the real absolute tail latency. And then the dark blue bar is showing the latency with our encapsulation. Blue right bar shows the latency without, our encapsulation. And as you can see, the gap between the two is very small. Even at the, P100 point, it's definitely less than 1 microsecond. So we've been using this stack on our A3 Ultra and A4 machines for the last, several quarters. And then the total traffic volume and the number of QPs that we, serve through this stack has been increasing significantly. And it has definitely reached, triple-digit terabps range. And then we also confirmed the overhead of this network virtualization, even at the workload level, such as nickel test or the true, training or distributed inference workloads level are small enough. So we confirmed that, for example, Llama 3 step time doesn't increase at all. Okay, so now I'm going to hand over this back to Weilong so that he can cover the ease of use portion.
Thanks, Chang. Next, I'll talk about 2 case studies of how we make the GPU NIC and network easy to operate and troubleshoot for both our customers and for Google. The first will be a feature called VPC traceroute. This is our first stop or go-to stop for troubleshooting. And second, I will talk about how we do in-service software upgrades without disrupting our customer traffic. Now let's look at the first case, the VPC traceroute. So the problem it is trying to solve is that, hey, your network seems to be broken. And we all know that there's a myriad of reasons why the network may appear to be broken and sometimes just not the network. So as the network operator, our first question to ask is it a network? And on one hand, we can do probing or traceroute in the hypervisor. This will cover the host-to-host network. The problem there is it doesn't exactly cover the whole VPC data path. For example, if you have a firewall rule misconfigured in the VPC, this hypervisor traceroute and probing actually doesn't cover that. On the other hand, we can do in-guest VM traceroute. This is the most authenticated data path, but the problem is Google does not have access to our customer's VM, and it is not tractable and scalable if we have to ask our customer to do this in every occasion. So the solution to this is we introduced a feature called VPC traceroute, where we allow the virtualization stack in the hypervisor to inject probe into the hardware just as if the probe comes from the VM. And then before we deliver this probe packet to the destination VM, we actually detect, intercept, and drop the probe packets, because otherwise, if it shows up in a VM, our customers would be very confused. The way that we make this happen is by utilizing the sample and drop bits in the PSP header. And if and only if both bits are set, we treat this packet as a probe packet that is sent from the hypervisor, and we would intercept and drop it and report to the control plane. And the pipeline that makes this happen is that we integrate with our existing control plane software, where we can craft such probe packets on demand in the software. And we inject these packets into the hardware, the same route pipe that handles the PSP traffic, with some metadata set to some magic value. In the hardware, we match for this magic value in the metadata, and if we see it, then we forward it normally to the PSP egress encapsulation and encryption, and after encapsulation, we send it to a special pipe where we set the drop and sampling bits in the header before we put it on the wire. At ingress, we match for the sample and drop bits in the PSP header first before we do decapsulation, and then we set some metadata if we see these bits are set. And then before we deliver the packet to the VF, we match for the metadata, and if we see it, we know this is probing packets, we drop it and send reports back to our control plane. So here you can see VPC traceroute in action. It integrates seamlessly with our existing CLI and web UI tools here at Google. And what this enables us is, with a single line of command, we can probe any pair of the GPU NICs in our network and see if there's actually a problem in the underlying network. Next, I will talk about how we do in-service software upgrades without disrupting our customers' traffic. As you can imagine, we need to occasionally roll out new versions of the software to bring in new features or bug fixes. The naive way to do this would be we just shut down the old version of the software and we kick off the new. And the problem with this is when we close the old software, the process closes, and the file descriptor that is associated with the process is closed, and the NIC resource cleans up, and the forwarding state in the hardware is gone until the new ASAP-D comes up and starts to programming the forwarding state in the hardware. The problem there is the new ASAP-D takes time to initialize, in our experience, about 20 seconds for 8 GPU NICs. That means for the 20 second, the GPU NICs doesn't have connectivity. This translates to RDMA QP timeout for user application. And this usually means the training job has to abort and it has to start from a checkpoint. And if you have thousands of VMs in a cluster, and if we do a rolling upgrade, this means the whole cluster is rendered useless for about hours. And this is clearly not acceptable. The way we do this is through hitless updates, or updating without disrupting our user traffic. So before the upgrade, our software, or ASAP-D, is running. It programmed the hardware with some forwarding state, and the packets are flowing through the hardware. When we want to roll out a new version, we actually start the new process in parallel to the old, and the new ASAP-D process will program a standby flow database in the hardware, or FlowDB2 in this picture, and no packets is actually flowing through this FlowDB2. And the new ASAP-D will take its time to initialize while the traffic is served by the existing FlowDB1 by the old version of ASAP-D. After the new version finishes initialization, we start the transfer of business state, or PSP tunnel state, from the old ASAP-D to the new. And new process starts to program the state into the hardware in the standby flow database. After its programming, at this point, we can switch the actual traffic to the new FlowDB2, and then we can safely decommission the old ASAP-D and the old FlowDB in the hardware. And next, I'll hand over to Chang to explain how this has helped us to roll out software upgrades seamlessly.
Okay, Weilong has talked about how we designed and then implemented the Hitless update capability. And then let me show you how it actually serves our workload seamlessly very well. So here in this graph, I'm showing you a time series. So the x-axis is time over about 2 weeks last November. And then y-axis is the number of machines hosting our different releases of networking or network virtualization stack. So different colors here represent different release versions. So as you can see, the total number of hosts running this stack has been increasing smoothly, and then the transition has been also very smooth without any hits. So this confirms that this hitless capability of ASAP-D has been serving us very well, especially with ML workloads. So to wrap up our presentation, we have today explained how we have properly virtualized GPU network, and then the performance and availability overhead is the most important thing, and then we explain how we handle those things. And this has been one of the most exciting capabilities that we have introduced on our GPU fleets. And then we've been receiving a lot of great feedback from our partners and customers as well. So thank you very much for being with us today.